Hi everyone. Today we're talking about the parallel axis theorem. So when we're working, what's that?
It's fun to have.
Oh.
Just interrupt your la 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 la.
So we have two different prefabs, right? We've got a long thin rod with the rotational axis through the center. Then we have a long thin rod where the rotational axis is through the end. So if it's through the center, you've got a moment of inertia of 1/12 ml squared. And if it's through the end, you have 1/3 ml squared. So it's a greater moment of inertia if it's through the end rather than on the center mass. Now, why is the prefab different for both of these, right? So the prefab is different because the axis of rotation is different, right? And that is because if you have mr squared is your moment of inertia, that means that you are increasing the radius for a lot of those particles, right? So if you're thinking of this particle-wise, the maximum radius that you could have was L/2, right? In both directions, you can only get L/2. But in this direction, you can have the full, you can have the full length available to you. So that allows you to have greater radius. And if you have greater radius, excuse me, if you have greater radius, then you're going to have a greater moment of inertia. Now it asks us to show the derivation of the moment of inertia of a rod rotated at its end. So first what I'll do is I will do the calculus part, and then I will show you the parallel axis theorem shortcut. So if we want this moment of inertia where the axis is on the end, you will do the integral from 0 to L of r squared dm. So if you'll remember, when we had to derive through the center, we started at a negative L/2 to a positive L/2, right? Because your center of mass was considered the origin, right? That was your 0. Because that's where your axis is. Here, our axis is on the end, so if we measure out all the way to the end, we're going to have, bounce from 0 to L, right? So that is why we have new bounds. Now we're going to integrate just like we did before, right? Lambda is dm over dr. You can also say that lambda is mass divided by the length of a linear object, right? So we will use both of those. You've got the integral from 0 to L of r squared lambda dr by multiplying that dr over to solve for dm. Now we will do the integral. You've got r cubed over 3 from 0 to L times lambda. So then you just have L cubed over 3 times lambda, but lambda is mass divided by length, right? As we showed up top. So that is going to eliminate some of those lengths. And then you have ml squared over 3, which you can see is the moment of inertia for a rod rotated about its end. Now, let's talk about the parallel axis theorem. The parallel axis theorem may not be faster for a one-dimensional linear density rod, but once you get to a three-dimensional object, this is going to be much faster. Okay? So the parallel axis theorem, first your axes must be parallel, right? So if we look at all of this, clear all of this stuff out, we start at the center of mass. Put that there. Start at the center of mass, then you go to the end, right? Those axes are parallel. You cannot make your axis now at some other angle. Okay? It must be parallel. So let's show you what the equation is. The equation is that if you have some center of mass moment of inertia, you take the moment of inertia as if it were at the center of mass, then add md squared if d is your distance. Okay, that is from the old axis to the new axis. Okay. So if we look here, if we have the center of mass right here, the distance from there to there is L/2, right? So that would be the distance in our parallel axis theorem for this scenario. So we will say that we've got ml squared over 12, right? That's the formula if it's at the center of mass, plus m times L/2 squared. So that is ml squared over 4, right? So you've got ml squared over 12 plus ml squared over 4. You can also say that's ml squared times 1/12 plus 1/4. You'll have to break that down. So 1/4 is 3/12. 3/12 plus 1/12 is 4/12. 4/12 is 1/3. So 1/12 plus 1/4 is 1/3. I feel like I almost developed a lisp there, trying to say twelfths and thirds and fourths. But then you get ml squared over 3, right? Which is, again, exactly where we ended up. Now, that algebra, you may feel like that's a little bit more complicated than the calculus, but trust me, when we get to three-dimensional objects, parallel axis theorem is much better than your calculus. For example, we have a solid cylinder rotating about its edge on an axis parallel to the center of mass. So let's draw a cylinder, okay? And the original axis is through the center of mass, like our prefab shows. But now it is rotating on the edge, okay? So now instead of kind of rotating about its center, it's kind of revolving around this imaginary axis on its edge. So our parallel axis theorem, since they are parallel, this will work. You've got I off a non-center of mass axis. You take the center of mass moment of inertia plus md squared, right? That distance here is just the radius of the cylinder, right? And the cylinder's moment of inertia is in terms of radius. That is mr squared over 2. Right? So we will say that this is mr squared over 2 plus m times d squared, so that would be times r squared. Right? So 1/2 mr squared plus mr squared is 3/2 mr squared. So that is the new moment of inertia for a solid cylinder, not a hoop or a shell, right? It is a solid cylinder rotating about its edge on an axis parallel to the center of mass. Now we have a solid sphere rotating about an axis tangent to its surface. So we have a sphere. The original axis was through the moment, the original axis was through the center of mass. Now it is tangent to the surface, and again, that is a distance r, right? So distance is going to be radius. Our moment of inertia from the center of mass for this is 2/5 mr squared. So the parallel axis theorem, we say that I for a non-center of mass object or axis would take the center of mass moment of inertia plus md squared. So that would be 2/5 mr squared plus mr squared. That's like 2/5 plus 5/5. So you've got 7/5 mr squared. So that's how you can do this for three-dimensional objects. Much easier than doing the calculus. Guarantee that for 3 dimensions. Now, let's not forget number 2. Number 2 says, why does the moment of inertia change depending on the axis of rotation? So the reason that it does that is because we are increasing the radius, right? We talked about that already. However, there is also the idea that you now have more mass off of your axis, right? So now that there's more mass off the axis and it's not so centered, it's going to take more torque to push the object or to create that angular motion, right? So it's going to resist a little bit more. You're going to have more mass to move, right? And this is supposed to be angular mass, right? Now, a challenge problem. We have 3 identical thin rods, each of length L and mass M. They are welded perpendicular, all perpendicular from one another. They are 90 degrees apart in every direction. And they are rotated about this axis of rotation that seems to be parallel to the y-axis, right? So our original was the y-axis. Now it has been moved to this new axis of rotation. So how we're going to do this, okay? It says calculate the moment of inertia of this monstrosity. What we're going to do is we're going to make a table to keep track of all of our information. So the idea is that you've got Ix rod plus I of the y rod plus I of the z rod. That'll give you the total moment of inertia of the system, right? So to get all of that, we are going to first need the prefab. Okay. That's really your moment of inertia from the center mass, right? Then we need the parallel axis theorem, right? You've got the md squared. Okay, that'll go right there. Then you've got the total. Okay, you're going to add up everything in your column, put it down in the bottom, and then add the totals all up, and you will get your answer off to the side here. Okay. So let's do this one at a time. Let's look at the X rod. Okay. The X rod is right here. Okay. I'll just make that a line. The X rod is perpendicular to the axis of rotation, right? It was originally through the center of mass of that rod. So we know that one. That is ml squared over 12, right? That is the moment of inertia of a rod rotated about its center of mass. Now that has moved, right? That has moved a distance of the radius, right? Or half of the length. So that would be L over 2. That will be the distance moved. So if you've got L over 2, squared is L squared over 4. So you have ml squared over 4, right? And remember, 1/12 plus 1/4 equals 1/3. So you will end with ml squared over 3 for the moment of inertia. So once you add those up, you will get ml squared over 3 for the X rod. Now for the Y. For the Y, we are now looking from a different perspective. The Y originally had the axis going through it, right? So that means that it's not actually rotating. Now, if this were a 3-dimensional object, yes, right? It would have a radius to actually rotate. But here, the radius doesn't actually matter. The length does. But since the axis of rotation is going through the length, then it doesn't actually rotate. It kind of just spins in place, right? It's just kind of doing this kind of motion, right? It's just kind of rotating back and forth. Okay? It's not actually rotating or rotating or rotating. It just kind of spins in place. Right? Spins like that. Really hard to do this. There's so much friction with this pencil. Anyway, so it initially has a moment of inertia of 0 because it's in the axis, right? So that's how it would work for a rod. For a cylinder, for a sphere, different ballgame, right? But we're talking about the thin rods. Now, that again moves a distance of L over 2, right? So now we have the same ml squared over 4, which gives you ml squared over 4. 0 plus ml squared over 4. Pretty simple math. Now this last one is going to be very similar to the x. Okay? The z-axis is right here. That's where the z-rod is going to be. And that is 90 degrees, so we can say that that is just like if the rod was rotating about its center of mass. So that would again be ml squared divided by 12. We can also see that the axis moved a distance of L over 2, right? So we will then have ml squared over 4. 1/12 plus 1/4 is 1/3. And a third plus a fourth plus a third is 11/12. So you've got 11/12 ml squared, and that is the moment of inertia of this complex system of identical thin rods. Right, that's the end of our video for parallel axis theorem, and in our next video we're going to move on with torque.